Hello, everyone. I'm a physiatrist. Does anyone know what that is? Raise your hand. Awesome. I didn't know what it was either when I was in med school. I'm a physical medicine and rehabilitation doctor. That means you see me if you've had a brain injury, a spinal cord injury, a stroke, things like this. So that's one hat I wear. I'm also a neuroscientist and a tech geek. So in my world, what I'd like to do is use neurotechnology to make people's lives better. And so I'll tell you a little bit about what Ian and I have been doing in this field since we met, I think, in 2013. Does that sound right? All right, so what's the problem? The problem is people are breakable. And so what we find is that things like car accidents, things like falling, can cause spinal cord injury. And the amount of impairment you get very much depends on what part of your spinal cord you break. So this is becoming a bigger problem in our country. It used to be that the most common cause of spinal cord injury was car accidents in younger males. Now, as we have an aging population, we actually are getting more and more older people who are falling. And because of arthritis and other things, they're injuring their cervical spine, their neck, and that's causing paralysis of all four limbs. And then you end up with people who can't take care of themselves. So one question I have is, what can we do about that? As we talked about earlier in the earlier presentations, home care is something that becomes necessary if a person can't take care of themselves. But home care is expensive. So as an example, we have about 17,000 new spinal cord injuries that happen every year. About 60% of those spinal cord injuries affect the neck area, meaning that people lose the ability to use both their arms and their legs. So what that means is about 175,000 people in the United States today have what's called tetraparesis, or the older term is their quads. Thinking about what it means to use your hands just in everyday life, or the opposite, not being able to use your hands, it costs about $40,000 a year to have somebody else do the things for you that you would do every day without thinking about it, using your hands, brushing your hair, brushing your teeth, getting dressed, making your breakfast, etc. So if we think about that, and we multiply that by 175,000, the American public is spending $7 billion a year on home care just for the people with cervical spinal cord injury. So the technology I'm going to talk about to you right now costs about $100,000 per person. But if you think about that on the scale of all these people, it pays for itself in 2.5 years. So what's the issue here? The issue is, depending on where you break your neck, depending on where your injury is, you need more or less care. So the higher up you break your neck, for example, Christopher Reeve, he was a very high-level injury. He needed ventilator support. He couldn't breathe for himself. In addition, he needed someone to take care of him 27 hours a day for everything. As you get down to lower levels, you can do more for yourself. Ian is a C5, and he'll tell you in a second about what that means for him in his daily life. But the point at which people can live independently and really can get away with very minimal care in their home is a C7, C8 level of function. And the difference here is two things. It's being able to grip and hold objects so that you can cut your steak. And it's the ability to transfer in and out of your chair. So one of the goals of the neurotechnology that we're working on is giving the ability to hold and manipulate objects back to people. So essentially taking people from a C5 level to a C7 level.
My spinal cord injury, like Marcy said, was a C5 level injury, which means I can move my arms decently well through my biceps, But essentially anything lower than my elbows, I can't move. So my hands are essentially paws. I can hold something together to pick it up like that, but I can't reach out and grab something with one hand. And as you can imagine, that really does limit what you can do for yourself. So I have someone that comes in the morning to help me get up and get ready throughout my day. I have someone sometimes that pops in through the afternoon to help me with little things, help me get some lunch together or whatever I need. And then also I need someone in the evening to help me get ready for the next day and get back into bed and all of that. So with this technology, it's trying to eliminate as much of that as possible so I can do as much for myself as possible.
So there are a couple different kinds of brain-computer interface technology. I'm just going to briefly give you an overview. You can use an EEG system, and that is recording the electrical potentials from a person's scalp. That's cool because you don't have to have surgery. You can take it on or off anytime. But it actually is a low information content signal. And so it's really hard to be able to control a lot of different things in your environment with that kind of signal. You get more information the deeper you go towards the brain. It's kind of like a microphone. If you're holding it in the back of the room, you can't really hear what's going on the other side of the room. But if you bring it all the way up to the stage, you can hear what's happening there. So the kind of implant we're going to talk about is one that's actually implanted in the brain. So Ian has a motor cortex brain implant with 98 electrodes that go down into his brain. That signal gets transferred, it's a lot of data, at a rate of 30 kilohertz. So 30 samples per second times 98 channels. And then a computer takes that, does some machine learning sorts of things to it to try to figure out what is Ian thinking. And then we use that pattern matching, basically, to control something that takes the place of Ian's arm. So there are different studies out there that are using this technology to return grasp to people. Some people will literally use a robotic arm. You might have seen the Pitt study with President Obama and Nathan, the gentleman on the top there, fist bumping. There's also another group who uses an exoskeleton, same concept. Ian, however, uses a system of electrodes on his forearm, and that actually stimulates the muscle into the pattern of movement that he's thinking about doing. So what you're seeing here on the left is Ian can't hold a phone. That's the point. And if you use the system, he can hold a phone and hold it up to his ear like an able-bodied person would. All right, how'd you get involved?
So no one plans to have a spinal cord injury. I certainly didn't plan it. I was an athlete growing up, but right after my freshman year of college, I dove out into a wave when I was on vacation, and it pushed me down into a sandbar, instantly breaking my neck. It was something I had done hundreds, if not thousands of times before playing in the waves, but it was just a perfect storm of everything going wrong. For me, that meant I had to go through and learn how to do everything again, how to eat again, how to live again. And I was just looking for more because I wasn't satisfied with the current rehabilitation that I was getting and what insurance said was enough. That pushed me to meet the team at Ohio State in Battelle and make the decision to have an implant on the surface of my brain that I didn't need. We used fMRI to determine what portion of the motor cortex to place the array. You can see right there on the screen, it's definitely very small. It's about the size of a pencil eraser. That's actually on the surface of the brain, and then it goes up to a little cap that I have protruding from my skull that when I'm in the lab we can actually connect to.
And this is an overview of how that system works. So the recording from those 98 electrodes sends basically voltage change information out at 30 kilohertz. And we do some wavelet analysis to basically make that signal more manageable in terms of big data, pull some of the features out of it that we then send to a machine learning algorithm. We've tried several different kinds. I'm going to kind of skip over that because of the technical details, but that gives us some decoder outputs. And the decoders are the things that we try to match with the actions that Ian is thinking about making. And you can see on the top there, that's what the setup looks like when Ian is training to use it. So in order to train to use it, he needs to think about the movements that he wants to make so we can tell the decoder when he's thinking what movement. And this is the end result of maybe about a year of training.
Yeah, so this is something fairly basic of reaching out, picking up a bottle, pouring the bottle into a smaller container, and then I reach over and change my grip and pick up something smaller to stir that bottle. Right here we're using dice because some of the engineers get a little antsy if we wanted to put water around all their electronics. But it shows something that's, really basic, and a lot of us, including myself, take for granted, but it's something that I can do. Now we're seeing where I can train on some standardized objects, but then take that and translate it into everyday objects.
So what you're seeing here are a couple different kinds of grips that Ian has learned to basically tell the computer that he wants to make. And he's able to generate enough force through this muscle stimulation on his arm to be able to hold the objects and do useful things. And the goal of this, obviously, is to take care of yourself, but also to be able to do leisure activities like play Battleship or drive a car. So what you're seeing here now on the top of the screen, MWP is the mean wavelet power. So that's the coefficients that we get out of the feature analysis that tell us basically which of the electrodes is carrying the information at that point in time. That gets fed into the machine learning algorithms and gives us an answer about what Ian's thinking about. So what you're seeing here is Ian driving a car simulator with his thoughts. And this is the same kind of simulator that is used with autonomous vehicles. And we're working towards being able to use this in shared control for some of these semi-autonomous vehicles. He's already used it to drive a little Model 4 GT with his thoughts. Obviously, there are a few safety considerations that we need to put into place before he gets into a car and drives it. The other major thing we need to do before Ian can get into a car with the system and drive it is make it portable and mobile. So what you're seeing on the top there is the setup in my lab. It's roughly the size of a large dinner table for all of the things that we need in order to record, interpret, decode what Ian's thinking, and then stimulate his arm. And then what you see down on the bottom of the screen is the next generation component, which literally is something that could hang on Ian's wheelchair and he could take with him wherever he went. So this is something that we've got some grants out to some institutions, and we're hopeful that people will be as excited about this concept as we are. Now, the one thing I want you to notice here is the computer there, the tablet PC. Does it look like it's from 2005? Yeah, kinda. So that's one of the limiting things here, is we need to integrate the much more powerful PCs that are out there, but they also need to be medically compliant so that we keep Ian safe. And some other challenges.
There's some things that I have adapted throughout the 9 years of living with a spinal cord injury to be able to do that I can do better than this system provides currently. It does provide, or it does give a little bit of kind of delayed response because the computer has to process what I'm thinking about instead of me doing it naturally. So on this test where you see the whole goal is to move blocks from one side to the other as fast as you can. It's something that I can actually, I've learned how to reach out with my arm and kind of scoop and pick up the object and move it. And I can do that much quicker than reaching out, getting it positioned, and making sure it's in my hand the right way since I can't feel where it is. And then thinking about, okay, giving the close command So then I can pick that object up, move it over, and then release the object. So there are some things that are definitely easier to do without the technology, but it does give me the strength of being able to reach out and pick up a book or some of those other objects that you saw earlier that I can't necessarily do one-handed or with my capabilities that I do have. Another big obstacle is getting that system down to the smaller size so that way we can use it outside of the lab. Right now it's only something that we can use in the lab, and our actual research is kind of on hold right now, waiting for some funding to continue. But it is something that the whole team is hopefully working to get so I can try at home, and then we can actually prove that it works and get it out to more and more people.
And we have a very large team of people who's behind this project. These are just some of the people from OSU and Battelle. And that's it. Thank you.